In this lecture, we're going to take a look at section 6.4. We're interested in testing for independence in a two-way table. A two-way table simply means we have two cross-classified variables, which generically we can think of them as row and column variables. Okay, so that's what the two-way table means. So what we're interested in this section is that whether there is any association, that is a statistical association between two qualitative variables. Okay, so this is what we call a non-parametric method for testing the association between two qualitative variables. The non-parametric or distribution-free methods are methods that make no assumption about the underlying probability distribution of the random variable. So that's why they're called non-parametric. So our test for what we want to do here to establish association between two variables is called a chi-square test, and that's what this word is. I know it looks like chi, but it's pronounced chi. So we use a chi-square independence test to test the hypothesis that the null hypothesis here is the hypothesis of independence actually. So the null reads or says that the two variables are not associated. Okay, so that's what the null hypothesis is. The alternative, on the other hand, indicates that perhaps the two variables are in fact dependent and that there is association between these two row-column variables in the two-way table. Okay, and the reason it's called a chi-square, it has to do with the probability distribution of our test statistic, the formula that we use in order to test our hypotheses. Okay, so chi-square test, you can Google it if you'd like to. We're not really going to work directly with the distribution, but rather the name of the distribution as it pertains to the independence test. Our assumption is pretty simple. Usually with distribution-free or non-parametric test, there's not a whole lot of assumptions. So most of them, almost all of them, assume we have simple random sample, and that's just about it. So in this case, our assumption are, well, we have to have a simple random sample. That's our ongoing assumption. And here are a couple of interesting assumptions. One is that the expected cell frequencies are 1 or greater. I know this doesn't mean anything at this point. It's like, well, what is the expected cell frequency? I'll explain these as we go through an example. And number 2 is that no more than 20% of expected frequencies are less than 5. Okay, in other words, we don't like when expected cell frequencies in the contingency table fall below 5. So 20% of expected frequencies should not be less than 5. So if you have, for example, a table that is 2 by 5, that will give you 10. 20% of that would be 2. That means only 2 cells in the table can have expected frequencies less than 5. If you have a 4 by 5 table, then there are 20 cells. That's 4 times 5. 20 cells in that table. 20% of 20 cells would be 4. That means 4 cells. That's a row-column combination in the table. Only 4 cells can have expected frequencies less than 5. That is rather an important assumption. If that assumption isn't met, that means the chi-square test may be invalid. Usually what happens is, like, what do you do at that is we try to combine or collapse some of these classes or cells to create bigger expected frequencies. Okay, so let's take a look at an example here, and then again, don't worry about the formulas. I won't even go through the formulas. The formulas are in fact in your textbook, your digital version of the textbook by Diaz. So in this example, at an umbrella manufacturing facility, umbrella handles are measured and then removed from the assembly line if they don't meet specs. A daily report indicates how many rejected handles were produced by each of 3 presses at the facility during each of 3 shifts. A quality engineer wants to determine whether press and shift are associated. So here's the data. The engineer performs a chi-square test for association to determine whether the press and shift that produce the rejected handles are associated. So we're going to use alpha 05 to test the hypothesis. So the null hypothesis here again is pretty generic as we have it up here. The null hypothesis says there is no association between these 2 variables. So that means there is no association between press and the shift. The press and the shift. There is no association between them. They're totally independent. Now here is actually the data. Now if you look at this data, you kind of see here, look at the machine 2, press machine 2 during the first shift. Look at how many rejected handles were produced during the shift. 76. Look at shift 2nd, shift 3rd. So there's something going on in that first shift. Okay. And other than that, if you take a look at, for example, machine 1, press machine 1, look at the shift, the number of bad handles are pretty stable here, right? 48, 47, 48. Okay, so it looks like that press machine 2, there's some issues with that press machine. See the variability between shifts as it pertains to a number of bad handles. Now, I'm going to go to Minitab in a moment and we'll run the chi-square test, but from the output that you're about to see, we actually want one thing from that output, and that is our p-value. Okay, now the output from the chi-square test in Minitab actually gives you 2 p-values, 2 separate p-values, but they're somewhat related actually. One of them is called the Pearson chi-square statistic, which is 11.788. Don't worry about formula where that came from. But the Pearson test statistic here, it ends up being 0.19. And look at the likelihood ratio chi-square statistic. This is the likelihood ratio here. This is the maximum likelihood ratio chi-square statistic. Is almost the same. See how close these 2 numbers are? In fact, the Pearson chi-square, this number, that number approximates the likelihood ratio on which this likelihood ratio test is based on. The likelihood ratio test is also called a G test. G here stands for goodness, so it's also called a G test. Okay, so both of those numbers turn out to be pretty close for most parts, and you can use either of those to make the conclusion. In this case, it makes no difference, but sometimes they're slightly off. Remember, the first number, this one, is an approximation of this one. And so based on this, we are going to reject the null hypothesis, right? Because our p-value is less than 0.5. So we're going to reject the null. And remember, the null said that the 2 are independent. The null here is hypothesis of independence. And the alternative actually says that they're not independent. There is some kind of association between the press machines and the shifts. And there you go. This is the conclusion I have. So the engineer therefore is going to conclude that those 2 variables are somewhat associated, and the performance of the press varies depending on the shift. Now, we will actually see the reason for that conclusion is press 2 actually. Okay, and this is what I have in here more about it. Okay, now before we actually look at our next example, and that's about it. That's all we wanted to do. So yes, there is some kind of association between the press machine and the shift in which those bad handles are made. So let's go to Minitab and actually try to do this example in Minitab. Okay, so here I have Minitab open, up and running. And I went ahead and imported that data. I simply copy and pasted it from my note into this. So here, the first column, machine ID. Remember, that's the press machine. 1, 2, 3. First shift, second shift, third shift, and these are the number of BUAD handles, umbrella handles. Okay. Now, in order to do a chi-square test for independence, we're going to go to Stat, go down to Tables, and then here is your options. We're going to do a test for association. There you go. And there it explains. Remember, categorical variables are qualitative variables. They're also called classification variables. So click on that. And I've already had some data in there. So let me remove these. Some of this data is had to do with our next example. Okay. So there you go. Now, make sure that you choose this option. Summarize the data is in a two-way table. And you click in the columns containing the variable. Don't worry about these extra variables that I have. These are, again, I have accident, yes, accident, no. These are for another example we're going to see in a moment. So for this one, the column containing the table columns, that would be for our column variable, which is shifts. So double click on first shift, second, third shifts. And down here, labels for the table, the rows are actually going to be the machine ID. Okay. This will be a descriptive, this option columns, a name for column category. You can just call it, oh wait, I dropped the third shift here. Good to know. Look, there you go. Make sure you have all three shifts clicked. Okay, so you can leave this alone or just give it a descriptive name for the columns. We're going to just say, whatever, let's call these shift 1, 2, and 3. Okay, that's going to appear at the top of the output. Now your statistics here, these are some of the things that are already pre-selected. Some of them I selected it. Most of them were pre-selected. I believe this is the one that's not automatically selected. So here's what we want to do. We want to definitely have this chi-square test. We want the counts, display counts in each cell. Display marginal counts. Marginal counts give you the row and column totals. Okay. And the statistics to display in each cell is we're going to get the expected counts, and don't worry about this other stuff. And click on this one, cells contribution to chi-square. That's a pretty cool option. And hit OK. And OK again. And there is the output. Now, just to, again, for this table, this is a two-way table. So the columns are shifts, shift 1, 2, 3. And the row variable is the machine press machine 1, 2, 3. So that's how we got the two variables. Now, 48, 47, these are row column combinations. See, second row, first column. Each of these is called a cell in that table. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9 cells. This is a 3 by 3 table. So there are 9 cells in this table. Okay. And here's the output that we were talking about. So it pretty much displays the kind of input we already had down here, just displays it again with additional information. Now, for this, like, what are these numbers, right? If you scroll down, right in here, cell contents, it tells you, or it tells us how to read the numbers in each cell. So the first number in a cell, like let's say this cell, 36, that first number is the count in that row column combination. Row 3, column 1. That would be the number of BUAD umbrella handles coming from machine 3 during shift 1, first shift, 36. Those are the actual observed frequencies, observed counts. So that's what that is. The second number in each cell is the expected count. And there you go, 4314. That is how many we would expect. And you can actually get this number 4314 if you wonder how that's done. It's pretty easy. You multiply the row 110, the column 160, in which 43 appears in. Row total 110, column total 160. Multiply these two numbers, divided by 408, the sample size, and you should get 4314. So let's say for up here, how do they get 39.96 expected frequencies? You multiply 143 by 114, then divide by 408. So first numbers are observed frequencies, second numbers are expected frequencies or counts, and finally the last number is the contribution to a chi-square statistic. So that's what this number is, 1.16. This one is 0 because look at the numbers, these are almost the same. So that's there's no contribution to chi-square from that cell. These contributions, the bigger they are, the more they contribute to the rejection of the null hypothesis. If you add 1.16, 0, 1.1, 1.62, 2.95, 0.3, 3.8, 1.18, 0.415, 0.3468, all of these third numbers in all the cells, you're going to get this number, 11.788. Okay, so there you have it. This is what the chi-square test looks like. So again, you're looking at this. The reason we reject the null hypothesis here is due to mostly these high contributors, or this one, machine 2, and the number of bad handles during the first shift. You see that? That's the biggest contributor to the rejection of the null. Next to that is this number. These two add up to almost 6.8. 6.8, that is out of 11.788. The sum of these third numbers would equal to this, not the one on the bottom. It will equal to the one on top. Okay. The bottom number is a modification of that. It takes a look at the natural log of expected frequencies and all that. So don't worry about this one. But the p-value are pretty much the same. And so that's what that is. So based on 0.019, again, we're going to reject the null hypothesis. So pretty simple again how this is done. So now with this, we're going to go take a look at our second example. Okay, so I'm going to get out of here and go back to my note, and we take a look at our second example. Okay, now let's take a look at our second example. In this example, interesting, simple but very interesting example here I made up. The question: is someone using a cell phone more likely to be involved in an accident? Okay. So in terms of our chi-square test for independence, we want to test the null hypothesis that there is no association between cell phone usage and the incident of having an accident. In other words, those two variables are independent. There's no association. Using a cell phone has nothing to do with whether you get into an accident or not. That's what the null says. Now, of course, as a research hypothesis, the researcher want to determine whether there is an association or not. We suspect that there is, right? Because of the distracted driver and all that stuff. So we're going to use the following sample information to answer the question using alpha 05. So there you have it. And here's the data. Those who use the cell phones, 25 out of 325 had accident, 300 did not. And for those who didn't use a cell phone, 50 out of 400, so twice as many, but the sample size is about, 30% more higher. So there you go. We want to decide whether these two are independent, or there's an association again between the cell phone usage and the incident of an accident. And let me go down to my chi-square. There you go. So this is what the chi-square test revealed. And I'll go to Minitab. We'll run this again together. So according to the chi-square here, the degrees of freedom, by the way, I didn't mention it in the previous one. The degrees of freedom is number of rows minus 1 times the number of columns minus 1. So that would be degrees of freedom for the chi-square test. Remember, you're not seeing the formulas for these, so we're pretty much going off of Minitab, and all we're basing everything is off of this all-important p-value. That's all we really care about. Okay. So, for this chi-square test, both Pearson, and notice how close these are. This is always the case. Again, just to make it clear, this number is an approximation to this one. Usually, this is a more powerful one to use, but they're pretty close to each other. Again, the formulas even for them are very similar, except the maximum likelihood ratio looks at the natural log of the formula for our test statistic. Okay. So, whichever we use, the p-value is pretty large here. It's not less than 0.05. So, we fail to reject the null hypothesis. Remember, the null hypothesis here is the hypothesis of independence. And I have it here. We're going to fail to reject the null hypothesis since p-value is not less than 0.05. Therefore, there is no, actually, to our surprise, there is no association between cell phone usage and getting into an accident. Now the data, actually, I did not make up this data. This is a legitimate data. I got it from another source. So there we have it. No association between those. And so this kind of association, establishing association or independence, we use chi-square tests. Now remember, we do not infer or we do not establish causation here. We're not saying that cell phones are causing accidents. Okay, even if there was one. We're simply supporting association or not. There is no causation here. We're not going to say this variable causes another one. And there you have it. So let's go to now Minitab and actually conduct this one in Minitab. I already have this data in Minitab, and I'll show you in a moment. And you'll see where that number 0.112 came from here. Okay. Okay, so here we are in Minitab now. I went ahead and put in or typed in the data in these columns, column 6, 7, and 8. Okay, so I have cell phone, and I entered the levels for that variable, whether the person used or did not use a cell phone. And for the incidence of accidents, yes, no, I have the numbers that we had from the sample data. And note, by the way, something interesting, because look at, these are not numbers, these are variables. So there's a C6 and then -T. I did not put that myself. Minitab recognized that these are texts. Okay, so T means text. So like machine ID, these are 1, 2, 3, but they're not really not numerical numbers, right? Remember, these numbers are ordinal numbers. So instead of machine ID 1, 2, 3, I can go oops, A is not valid numeric. Well, because it's already, never mind, because it's already formatted as a number here, so don't worry about it. But anyway, when you first initiate these, if you put in as text, then the Minitab sees these as text. Okay. But again, I just want to emphasize these numbers 1, 2, 3 were not used anywhere in these computations. Okay, these are just labels. So let's run the chi-square test for association for this cell phone data. So I'm again going to go to Stat, Tables, chi-square test for association, and remove these. And here I have accident yes, accident no. The rows are let's see, what were the rows? The rows were a cell phone usage, right? Whether they use cell phone or not. So now for column here again, the columns are, I'm just going to call it incidence of accidents. Okay, whether they had it or not. Our statistics, we're going to keep the same information we had before. So hit OK. And pretty much that's it. And hit OK again. And there you go. This is the run of Minitab for this chi-square test. So here's incidence of accidents. Remember the column labels? That's what these are. These are the columns. Accidents, yes, no, and whether they use or did not use cell phone. These are the marginal totals: 325 total cell phone users, 450 did not use cell phone. 75 accidents, 700 no accidents, for total 775. The sum of these two numbers is 775, so is the sum of these two numbers, 75 and 700. So remember the cell contents. First number is a count, then it's an expected count or frequencies, and this is the contribution to chi-square. Now our chi-square statistic, think of it like Z and T, all those numbers, although they're different, but they're test statistics, just like the Z score, T scores. So it's a chi-square score. And when you add 1.3, 0.14, 0.95, and 0.1, those numbers do not add up to a large chi-square. In fact, there you go. The chi-square is only 2.52. And for this one, again, we don't have a large chi-square, so our p-value is rather large. Notice the p-value, there's more of a discrepancy here than it was before. And there you have it. Okay, that's because, again, the levels of these variables, there's not as many as the other one. And of course, sample size has to do with it too. So either way, we can use either Pearson or likelihood ratio. Either way, usually these are very similar. And p-value is large, so at 0.5 we're not going to reject the null hypothesis. But that 0.112 is exactly what I had in my notebook. Okay, and there you have it. So again, a very powerful test, and this is very few tests that handles qualitative or categorical variables. And also with the power of this test is that it shows you the contribution to the rejection of the null hypothesis. If you do reject it, you can pinpoint the source and the cause of rejection, something we could not do with a Z or a T test. Okay folks, so that will wrap up this lecture. We are done with this lecture, so I'm gonna go ahead and stop this video.